Good afternoon, class. We are looking at exam 2 review covering sections 3.2 to 3.5. We've looked at logarithmic properties. I've reminded you of those. And the very first thing you need to remember is if you can go from one format to the next, from the logarithmic format to the exponential format and vice versa, then I have an easy time with all of these properties. And remember, log is simply an exponent. When this is general form, when we go to a specific case such as natural log, the base is e, we get those properties. We can go to common log when the base is 10. And this is the change of base formula. Also, the relationship between exponential and logarithmic functions is such that they are inverse of each other. Therefore, when you graph them, they are symmetric with respect to the line y equals x. As far as differentiation formulas, we started with the definition. Then we had some basic differentiation formula involving a constant power rule, exponential functions, trigonometric functions. We added the product rule, the quotient rule. From the composite function, we looked at the chain rule, and of course, an example of that would be an extended power rule, and we are going to look at some examples now. So to do this, this part, take a derivative of f of x equals to x to the power of 5 over 9, x to the power of 9. This part, we use the quotient rule of exponential, and it becomes x to the power of 5 minus 9 or negative 4. So you do the algebraic technique first. Now to differentiate this, we say 2 over 9. We multiply it by negative 4. And then the exponent minus 4 minus 1 becomes minus 5. This is minus 8 over 9. X to the power minus 5 goes down, and it becomes x to the power of positive 5. For part B, anytime you have a fractional expression or a rational expression, you ask yourself, can I simplify? And in this case, anytime you have one term in the denominator, all you have to do, make up a number of fractions. In this case, we're going to make up two fractions. The first one gives us 10. The second one gives us minus 7x. And the derivative is simply minus 7. To take the derivative of an exponential function, I'm going to remind you the derivative of e to the power of x is itself. The derivative of e to the power of kx is itself times k by the chain rule. The derivative of e to the power of g of x is itself by g prime of x times by the chain rule times g prime of x. And if it's a to the power of x is itself a to the power of x times ln a, this is by the logarithmic properties. Therefore, when we have b to the power of x, we represent b as e to the power of ln b, and we replace the b with that. When that happens, as you know, ln b is simply a number, and by the power rule here, m times n, so ln b times x, where ln b is just the number, so e to any power, the derivative is itself, and this just, you can think of ln b as k and times k, or ln b. You put this back in the same format you received it, and that's the final answer, itself times ln b. If you happen to have f of x here, we also tag along f prime, which makes it a chain rule. So This is an exponential function. The answer is itself. The base is E, no, times ln2. Is this x or t or theta? No, times 7 by the chain rule. And you rewrite. Anytime you deal with sinusoidal functions, the methodology that you use is very simple. You say cosine and you pause. Therefore, y prime is negative sine because the shell function, the outer function, the main function is cosine. But this is the argument of cosine, and every sinusoidal function must have an argument, otherwise it's meaningless. So we use the same argument. Now, what is the derivative of that by the chain rule is 2, and we rewrite the answer, and we are done. For the second one, if you rewrite it as cosine x to the power of 2, may be easier to see what the answer is. So y prime is by the extended power rule. And again, I would write the formulas from my memory and I would apply that. So I would write the extended power rule and I would say I need 2, then I need cosine x to the power of 2 minus 1 over 1. And then by the chain rule or the extended power rule, I need the derivative of cosine, which is negative sine, and I rewrite the whole thing. So negative 2 cosine x sine x. Some of you may recognize this as minus sine 2a. You don't have to write that, but you may recognize this as minus sine 2a, in this case 2x, because sine 2a is 2 sine a cosine a. We do the same thing here. We're going to say cosine, and we are going to pause. That means the main function, the outer function, the shell function is cosine. The answer must be negative sine. Again, we need an argument. We put that, and the chain rule says you need the derivative of the argument, which is 2x, and you put the 2x in front, becomes minus 2x sine x squared. Most of these questions are either from your lecture or some of these mixed derivative practice test exam reviews that you've had. For example, these are from mixed derivative practice test. Sine squared of 8x. So let's rewrite it again, just to make sure we understand what we need to do. We are looking at the extended power rule. So 2 sits in front times sine 8x to the power of 1, or simply sine 8x. So that's n g of x to the power of n minus 1. That's this part. Now I need g prime of x. Sine 8x. Let me write that here. So I want to make sure that everybody can see that. Now I need the derivative of sine 8x, which means I need cosine of 8x, right? Cosine. So sine gives you cosine of 8x, and then the derivative of 8x. So I need cosine of 8x. Then I need the derivative of 8x, which is 8. And all I have to do, rewrite the whole thing. 16 sine 8x cosine 8x. F of x is 3x times 3 to the power of x. I want to differentiate that, and that uses the product rule. So I'm going to just write this as f times g, and this time I'm going to write the product rule for me right here. I'm going to write the product rule and I'm going to follow that. So I need 3x to be differentiated to get f prime. So I need 3 times g, just 3 to the power of x. And I need g prime. What is the derivative of 3 to the power of x? Since it's an exponential function, it's itself. Is the base e? No. By logarithmic properties, I need ln of the base, so ln of 3. Finally, I need f g prime f 3x. And I'm done. I'm going to rewrite this. I want you to notice if I put number 1 here, this makes it 3 to the power of 1 plus x or x plus 1. Therefore, for the second piece, this one and this one will do exactly the same. So this is 3 to the power of x plus 1. The second one is the same thing, 3 to the power of x plus 1. And what is left? ln 3 and x. We write it in this fashion so we can factor out the common factor of 3x plus 1. So if I take this one out, this just gives me 1. If I take this one out, this gives me ln 3 times x. The way we write this is x ln 3 because if I put the x after 3, 1 may be under the assumption that it's ln of 3x. So either write it in this fashion or x ln 3 is a better format. We continue with more differentiation. Again, I'm going to the raised dot here. That means I'm going to use the product rule. I'm going to write this as f times g. And I'm going to use the product. So I would write the product rule and I follow that. X to the power of 4 gives me 4x cubed times g or e to the power of 2x. Plus e to the power of 2x gives me itself because it's exponential. So e to the power of 2x. And then 2x gives me 2 because of the chain rule times f, which is x to the power of 4. And again, we're done with calculus. We're going to continue with algebra and factor. So what is in common? You can, if you want, you can rewrite this as 2x to the power of 4 e to the power of 2x. So you can see it, or you may notice that we have two numbers, 4 and 2, so 2 is in common. We have x cubed and x to the power of 4, x cubed is in common, and these two are identical, so you pick one of them as a common factor. So we need to simplify by dividing this piece by this piece. Notice this goes away, 4 divided by 2. That gives us number 2 here, everybody. Whereas this one, when you divide it, e to the power of 2x goes away, 2 goes away, and x to the power of 4 divided by x cubed results in x. This is the final answer. Please understand, this is just algebra and factoring. To do this, we are going to do the same thing, f times g. And we continue using the product rule. So f prime is 9 times the second piece, gx minus 1 to the power of 4, plus. Now we want to differentiate this piece. X minus 1 to the power of 4 is 4 times x minus 1 cubed. I'm using the extended power rule, times the derivative of the inside. The derivative of the inside happened to be 1, but I like to write it to make sure everybody understands we have to pay attention to that in case it's not 1. And then finally, g prime f. So I put the f or 9x. And again, I'm done with calculus. This is the end of calculus. I'm going to finish it off by factoring the common factors. As you can see, number 9 is in common. As you can see, x minus 1 is in common. This one has exponent 3, this one has exponent 4. You choose the smaller of the two. 9 times x minus 1 cubed is the common factor, everybody. So what happens? From here, if we divide it by this piece, we get x minus 1. From here, if I divide it by this piece, this goes away, 9 goes away, 4 is left, and so is x. So the second piece gives me 4x. And obviously x and 4x, they add up to 5x. And that's the final answer, everybody. We continue with the differentiation. And again, we're using one of the questions from the mixed derivative practice. This uses the chain rule in conjunction with the quotient rule. So something to the power of 3. First, I'm going to go with the extended power rule. I put the 3 in front. Then the same thing, 4x over 2x minus 9 squared, according to this. And finally, I need the derivative of the inside. So I'm going to use the quotient rule by calling this f over g. So I need a fraction bar. F prime is 4 times the bottom 2x minus 9 minus g prime f. G prime is 2 times f, the top is 4x. And then I put the bottom in a parenthesis and square it. And again, this is the end of calculus step. Now, first, let's simplify this. 8x minus 36 minus 8x. These two cancel each other. So if we go with a fraction bar, what is at top? Number 3. 4x quantity squared and minus 36. Please understand, this is 4x to the second power over 2x minus 9 to the second power. So what's in the denominator? 2x minus 9 to the second power, and then 2x minus 9 to second power. You add up the exponents, you get 2x minus 9 to the fourth power. So here's 3 at top, here's 4x quantity squared at top. This whole thing is negative 36, and this one has a exponent 2, the same thing here, they add up to 4. And now, of course, this is 16x squared. The product of these 3 gives us minus, see we have the sign negative, 1728x squared in the numerator. You want to differentiate this using the quotient rule. We're going to write f over g. So we are going to go with f prime g minus g prime f over g squared. And please understand this is cosine. The derivative is negative sign. So cosine and pause, negative sign. Negative sign of what? Whatever the argument is, negative sign of 5t. So cosine gives you negative sign with the same argument. Now, if this is t, we're done, but it's not. By the chain rule, the derivative of 5t is 5. And that's f prime. What about g? Times g, which is the denominator, which is 5t. Minus g prime f. You need the derivative of the denominator, minus 5, and then times the top cosine 5t. The bottom, you just write it and square it. Becomes 25t squared. You notice we can take a common factor of 5 or negative 5 from the top. And of course, I put the 5t in front, okay? Because you don't want it to be after sign of 5t. This negative remains, this 5, number 5, goes away, and this 25 changes to 5. Again, negative remains. This 5 goes away. This 25 changes to 5. Anytime you're dealing with a rational expression or fractional expression, the first question is, can I simplify? In this case, if you can simplify, meaning the top must have a factor of x plus 3, because if it has any other factor, it doesn't help. And so two is a prime number, so you have x and 2x. And then all you have to do, I'm assuming we are okay with the factoring, work on number 9, which is the product of 1 and 9 or 3 and 3, and make sure it works. When you look at the middle term, this gives you 6x, this gives you 3x, and the sum must be equal to 9x. It works. The answer is 3.
All right.
And the derivative is 2. Now, what I want you to notice, if you were to use the quotient rule, you would get to the same answer. But it's really not a good idea because this is much easier. Okay, everybody? Anybody wants to read this question for us, please? Okay, nobody? The growth in world population in million is estimated by the formula P of t equals 3100 e to the power of 0.0166 t, where t is the number of years since 1960. Find the instantaneous rate of change for the year 2015, include units. Number 1, anytime they're asking for the rate, if 1 point in time is given, that means instantaneous. If 2 points in time, it means average. Number 2, whenever you're doing word problem, you always answer it with proper units back. So we are going to differentiate this. So P prime of t, you write the 3100. E to the any power, the answer is itself. And then by the chain rule, the derivative of the exponent gives you the number 0.0166. You multiply by it, and the product of these two numbers gives you this. And now from 1960 to 2015, there is a difference of 55. You replace the t with that, you put it into a calculator. And it gives you this answer. As far as the number is concerned, you really have to understand the units. This is dp dt, the change in population over change in time. So 128.2273 million people per year, or 128 million, 200,000, 220,730. What I want to mention is that, again, the units follow that. Okay, it's extremely important. Also, what it means is that after the year 2015, or on the year 2015, the population of the world is increasing at this rate because it's a positive value, means increasing. Anybody wants to read this question?
The length of a growing Tasmanian devil is estimated by the function LW equals 2.265 W to 2.543rd power, where W is in kilograms and L is in millimeters. Its weight can be estimated by w to t equals 0.125 plus 118 t, where t is its age in weeks. How fast is the length of 30-week-old Tasmanian devil changing?
Excellent. So they're asking for the rate when they say how fast. They're asking for the rate. 1 point in time, instantaneous rate of change to derivative. So when we go with the Leibniz's notation, dy dt is dy du dt. In this case, the length, so dl dt. And with dl dt, we write it in the same manner. What is the intermediate variable from length to time? In between is the w or weight, so dw. So we take the derivative of the first piece, this one, is this number, 2.265, times the exponent, this number, 2.543, times w to the power of the same thing minus 1, 1.543. So that's dl dw. And then dw dt is very simple, just 0.18. And so we multiply this number, and this number. We get 1.0367811. I use a lot of decimals. You have to realize you have to go with a lot of decimals. It's at the end that you do the rounding according to what they ask you. And of course, now, what about W? Well, you have two choices. You can replace it with this, and then T is 30. Or just evaluate this when T is 30. So when we do that, again, that's an easier way, sort of. Now we can replace that with 5.525, put it into a calculator, do the math. 14.4912 almost means 14.5. That means when the Tasmanian devil is 30-week-old, is increasing, the length is increasing by about roughly 14.5 millimeters. Now, you can find L as a function of T, which means replace the W with this, and then differentiate that. If you remember, this is the Leibniz's notation. This is finding the composite function. And if you do that, then L prime or dl dt, we write this number. Then this uses the extended power rule. You put the exponent in front, the same thing to the power of subtract 1, 1.543. And then by the chain rule, the derivative of the inside, which is simply 0.18. Okay, so this one and then 0.18. The product of the three numbers is the same as what we got here, 1.0367811, and the parenthesis 0.125 plus 0.180 to the power of 1.543. And of course, if you want to find it in 30 weeks, just plug the 30 here, and it will give you the same answer. By the way, they didn't ask for the length when the Tasmanian level was 30, but you could just plug in and find L of 30. How do you find L of 30? Just this number, if you plug it into this formula. This formula, you can, because you have to find this and then that. Or into this formula, replace it with 30. Either way, you come up with the answer, in case they did ask and they have. Okay, that's where it comes from. The graph of a function f is given in the figure. Use it to sketch the graph of the derivative of f prime. I hope you remember that. So I'm going to remind you of a few things. The peaks and valleys, decreasing, increasing. What are they? Relative extrema, relative max and mean occur where f prime is 0. So if you were to draw tangent lines would be horizontal tangent lines. And where f is decreasing, okay, f prime is negative. When it's increasing, f prime is positive. And as you look at this one, at A, B, C, we put those small tangent lines, a line segment to represent the slope is 0, and that means they correspond to x-intercepts on the graph of f prime. This point, again, very carefully, they have drawn, you don't have to worry about it, a line segment, which is a tangent line. They pick two points and they have calculated that. Now, as you can see, this is decreasing, this is decreasing, this is increasing, this is increasing. So we're going to write decreasing means f prime is negative, and increasing means f prime is positive, and corresponding to A, we have A prime, B, we have B prime, C, we have C prime. Those are the important points. And then if you graph it, notice what happens as expected, class. This part is decreasing, so it's below the x-axis. This is increasing. It's above the x-axis, but it has to come back down because at B, we have B prime that becomes negative, and over here is decreasing again below the x-axis, but it has to come back up, and the rest is increasing and therefore positive and above the x-axis. And as far as this point is concerned, 5, 3/2 or 1.5 would be on the graph of the derivative function. The graph of a function is given. Use it to sketch the graph of its derivative f prime. First, reminding you that a function fails to be differentiable if it has a sharp corner, discontinuity, or a vertical tangent line. So please understand you have 1, 2, 3, 4 line segment, and all you have to do, if you assume that these are the pairs, calculate the slope, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So for this one, for example, would be 0 minus 1 over minus 1 minus negative 3, which makes it negative 1/2. If this is negative 1/2, this must be positive 1/2. This you can easily see and calculate it. The slope is 1. This one is negative 1. We've gone through that. And so just for the sake of argument, if you're looking at this one, okay, and you assume you have a line, then the derivative of the function f prime has a horizontal line with the equation y equals negative 1/2, and it goes indefinitely on both sides. However, it stops here. So at this point, we have a sharp corner, we have a hole. Now, if you write the rest of them, so y equals 1 would be this line, continues indefinitely on both sides. However, at this point, we have a hole. At this point, we have a hole. And the rest of them follow in the same manner. Find an equation of a tangent line to the graph of the following function, where f of x or y is x squared minus 3x minus 1. So we need to find two things, a pair and a slope. So first and foremost, if we differentiate this, we get 2x minus 3. Now, if we plug in 4 into the function, 4 squared 16 minus 3 times 4, which is 12, makes it 4 minus 1 is 3. We have the pair. If you plug it into the f prime of x, the derivative of the function, we get 5, and that's the slope. So y minus y1 equals m times x minus x of 1. So y minus 3 equals 5 times x minus 4. And that gives us 5x minus 17. We've seen this before, of course. So this is 5x minus 20. And when we move this, we get plus 3. Again, this is important to know. This pair belongs to the original function, belongs to the tangent line. It's the point of tangency. And therefore, if this is correct, which it is, if you plug in 4, you get 3. This means this process was right, has got nothing to do with this. We want to differentiate this, as you know, we have to first replace this with x to the power of 1/2 and write it in an exponential form. Then we're going to multiply these two, we're going to distribute, and this is x to the power of 1. When we don't write the exponent, everybody, the exponent is 1. So 1 and 1/2, they add up to 3/2. So x to the power of 3/2, the rest are very straightforward. To differentiate these 3/2 sits in front, we are looking at the simple power rule. 3/2 x to the power of 3/2 minus 1 is 1/2. And this is 5. And we change this to the square root of x. So it looks the same. I'm going to differentiate this. And again, what I'm going to do, I am going to change the square root of x to x to the power of 1/2. And then I'm going to put a raised dot in between, meaning I'm using the product. As you see, according to the product rule, I need f prime half of x to the power of 1/2 minus 1 is negative 1/2. By now, everybody knows that. Times g, which is e to the power of x, plus g prime f, the derivative of e to the power of x is itself, times x to the power of 1/2, or just square root of x, however you want to write that. You can even write square root of x right here. So this is square root of x, and everybody knows that. This is going down, x to the power of positive 1/2 becomes square root of x. So again, this is the only calculus step. So we're going to have a couple of algebraic steps. You can write a big fraction bar and take a common denominator and do that, or just notice if you want to take a common denominator is this one, so multiply this one by 2 square root of x over 2 square root of x. Please understand that this expression equals 1. So what happens in this case, when we multiply, just keep this one and multiply these two pieces, because this would be the fraction bar, right? Just multiply these two pieces and you get 2x. Okay. And of course, if you take out this piece, which is in common, you get 1 plus 2x. We are going to use the quotient rule on this example. So we are going to write f over g, and therefore we follow the quotient rule. F prime is itself e to the power of x times g, which is the denominator, 1 plus x, minus g prime, the derivative of the bottom is simply 1, times f, that means the numerator. And just write the denominator and in a parenthesis and square it. And we are done again with calculus. All we have to do, just simplify the numerator. This is e to the power of x. So e to the power of x times x. This is minus e to the power of x. And needless to say, these two cancel each other. We write this as x times e to the power of x. That's the better way of writing it. By the way, I also put this so to remind you of all of the formulas. For example, the square root of x to the power of 1/2 and so on. Over here, we are going to do the product rule again. And I hope you remember that I've mentioned that because we've done this, because if 5 is a huge number or decimal fraction, you can put brackets and just work on x. The derivative of this is 5 times the second piece, 3x minus 2 to the power of 4. The derivative of g, so we are looking at this, is 4 times this to the power of 3, and then times 3, and finally times f, or 5x, and we are done with calculus. As you can see, 4 and 3 and 5x, the product is 60x. Now, between these two pieces, we want to do the factoring. 5 is in common. 3x minus 2 has exponent 4 here, exponent 3. We go with the smaller of the two. And the common factor would be 5 times 3x minus 2 cubed. You divide this one by this one, this gives you 3x minus 2. You divide this one by it, 60x divided by 5 gives you 12x. And so all you have to do, add the 3x and 12x to get 15x, and that's the final answer, everybody. Anytime the numerator is a number, we don't have to use the quotient rule. We bring it up using those exponential rules, and we are going to use the extended power rule. First, we need -4. Then we need the same thing to the power of -4 minus 1, which is -5. Then we need the derivative of the inside, 14x minus 1. We are done. We're going to take this down. So we make a fraction bar. We take this down, make it +5, and everybody's happy. Very straightforward, everybody. All right. F over G, we use the quotient rule. F prime, so fraction bar, F prime is 1 times the bottom 2x minus 1 to the power of 4 minus G prime. We want to differentiate this. So 4 times 2x minus 1 cubed. By the chain rule, the derivative of the inside is 2. And then G prime F, put the X next to it. The bottom, just write this to the power of G squared, so to the power of 4 times 2, 8. Done with calculus. We are going to simplify. So notice 2x minus 1 is in common. This has exponent 4, this has exponent 3. We're going to go with the exponent 3. The first piece leaves us 2x minus 1. What about the second piece? If 2x minus 1 cubed is gone, it leaves us -4, 2x. The product is -8x. So the first one leaves us 2x minus 1, and the last one leaves us -8x. Needless to say, this cancels out this one, and number 8 changes to 5. Everybody, this goes away completely. This becomes 5. And the top, they add up to -6x. And we are done. So -6x minus 1. We want to differentiate this as always. When the numerator is just a number, bring this up. This is x squared plus 3 to the power 1/2. Bring it up, becomes -1/2. Algebra. We are going to differentiate this. So the 4 is a multiplier, you keep it, and this one you use the extended power rule. So we multiply it by -1/2. Same thing to the power of -1/2 minus 1, or -3/2. And then the derivative of the inside is 2x. And we're done. We are going just to rewrite this, everybody. So 4 times -1/2, -2 times 2x is -4x. This one goes down, and you write it as +3/2. So this becomes minus 4x over x squared plus 3 to the power of positive 3 halves, and you change it to a square root as the final answer. To differentiate this, again, reminding you that whenever you deal with the sinusoidal function, it's important to know what is the shell function. And the way you know what's the shell function, I would read cosine and I would pause. That means cosine is the shell function, the outer function, the main function, and the derivative of cosine is negative sine. Okay? But you have to have an argument. So it's the same argument, 3t to the power 4. And then by the chain rule, the derivative of the argument is 12t cubed. In a sense, we are using this one or this one, if you will. Take a look. Minus sine of g of x, g prime of x, and you put the 12t cubed in front, becomes negative 12t cubed sine of 3t to the power of 4 as the final answer. As always, anytime you have a fraction, you're going to ask yourself, can I simplify it? So as you notice, this gives you x. So we make up two fractions, and this gives you 4. And now we can use the extended power rule on that, which becomes 6 times the same thing to the power of 5 times 1. Let me just write it for you. So this becomes 6 times x plus 4 to the power of 6 minus 1 or 5 times the derivative of the inside is 1. Therefore, this is your final answer. As for this example, we are dealing with the combination of a chain rule and a quotient rule. So something to the power of 5, you start with the extended power rule. So you start with 5. Then you write the same thing to the power of 5 minus 1 or 4. And now g prime of x, the derivative of the inside. So I'm going to call this f over g. And I'm going to use the quotient rule, f prime g minus g prime f over g squared. So the top gives me 2 times x minus 8. So 2 times x minus 8 minus g prime. The bottom gives you 1 times the top minus 1 times 2x plus 3. And I just write the bottom x minus 8 in a parentheses and a square. So first and foremost, let's simplify the numerator. This is 2x minus 16 minus 2x minus 3. As you can see, 2x minus 2x cancel each other, so we end up with negative 19 in the numerator. Now, to make sure you see what's in the numerator, if you have a huge fraction, 5 is in the numerator. This one, we're going to write 2x plus 3 to the power 4 over x minus 8 to the power 4. I want to separate them so it becomes clear what you're dealing with. And this one is obviously negative 19 over x minus 8 quantity squared. So if you have a huge fraction bar, this at top, this at top, this at top. The product of these two is negative 95. The product of these two is x minus 8 to the power of 4 plus 2. 4 plus 2, which makes it 6. So 5 times negative 19 is negative 95 times 2x plus 3 to the power of 4 over x minus 8 to the power of 6 as the final answer, everybody. I'm going to differentiate a bunch of exponentials, and I'm going to quickly remind you, it is always itself. So y prime is e to the power of 10x times what? The derivative of 10x. 10. We put the 10 in front. What happens to the second one, part b? E to the power of 10x is itself times what? The derivative of 10x, secant squared x. What about y to the power of y equals 3 to the power of x? It's an exponential itself. Is the base e? No. I need ln 3. Since this is x, we don't need anything else. And the final answer is 3 to the power of x times ln 3. It's very straightforward, everybody. Let me remind you of one of the examples we did again for the sake of a Leibniz's notation in essence. Example 16. Observations show that the length L in millimeter from nose to tail of a Siberian tiger can be estimated by the function L equals 0.25 W to the power of 2.6, where W is the weight of the tiger in kilograms. Furthermore, a young tiger's weight can be estimated in terms of its age in days by the function W is 3 plus 0.21 T. I hope you remember we've done that. So how long is it after 100 days? When it's 100 days old, so you just, if you plug in 100 here, you find the weight, right, everybody? And if you plug in the 24 here, you find the length. This is elementary algebra. You plug it into a calculator and you do the math. At what rate is the length increasing when it is 100 days old? That means take the derivative because there is one point in time. So we're going to write dl dt, the intermediate variable from L to T. In between is the weight, so dw. And the LdW is very simple, 0.25 times 2.6 times W to the power of 1.6. And the WDT is simply 0.21. And if you multiply these three numbers and you put it in front, you have this function. Now, you have two choices. You can replace the W with this, 3 plus 0.21 T, and becomes a function of T, and replace the T with 100. Or, since we've already calculated W, the weight when the T is 100, just replace the W with 24. And because we are calculating that, that's faster. So what it means is that the tigers is increasing length by this much, 20.20532 millimeters per day when the tiger is 100 days old. If we wanted to go with a composite function, everybody, we would write L as a function of T. That means replace the W with that. And now L prime of T, or dl dt, would be the derivative of this one, which is using the extended power of 0.25 times 2.6 times the same thing to the power of 2.6 minus 1 over 1.6, the derivative of the inside, which is 0.21. Okay, so first of all, that's L of 100 that we found here, by the way. Okay, which was 969. But the differentiation, as I mentioned, uses that. And if you multiply the three numbers, you get the same number, by the way, here. And at this point, if you replace the T with 100, you must get the same answer here. Okay, everybody? And I'm going to quickly remind you of the next question that, again, we just did it in class. The amount of glass recycled in a community is G of P equals square root of 0.5 P squared plus 7 tons. Where P is the population in thousands. It is estimated that that T years from now, the population of the community will be P of T equals 4.4 plus 0.1 T squared thousands. How many tons of glass are expected to be recycled 4 years from now? And so basically the same thing, you replace the T with 4, and that gives you the number of people, 6, and it's in thousands, so 6,000 people. Now you put that into this function. Again, we have done this class. And this is 36. Half of it is 18. plus 7 is 25. Square root of that is 5. 5 tons of glass. So the first part is elementary algebra. Now you want to find the rate. We are going to go with the Leibniz's notation, the rate of what? Change of glass with respect to time, right? Find the rate at which the amount of glass recycled is changing with respect to time 4 years from now. So we want dg/dt, which is in this format, and the intermediate variable from g to t is p, the intermediate variable. So you put the dp. So you differentiate this with respect to p. To do so, we're going to write this to the power of 1/2. And now we use the extended power rule 1/2 times 0.5 p squared plus 7 to the power of negative 1/2, and then times the derivative of the inside, which is 0.5 times 2p, which is p. And then dp dt is just 0.1 times 2t, or 0.2t. Now we're going to use p equals 6 and t equals 4 because we have done the calculation. We plug in. I've shown you the evaluation before. As you recall, this is 25 from here, class. This is 25. 25 to the power of negative 1/2 means 1 over square root of 25 means 1 over 5. So this part, okay? So 1/2 times 1/5 times 6 times 0.8. And this is 4.8 divided by 10 is 0.48 tons of glass per year. Tons of glass per year. Now, of course, I can replace the p with this, and I have g of t equals square root of 0.5. The parenthesis 4.4 plus 0.1 t squared to the second power plus 7, and work on this differentiated and everything else. But most likely this is more complicated than using the Leibniz's notation.